Hello, everybody, and welcome to my presentation. My name is Albert Dunford with Powersim. We are showing now today the link between JMAG and PSIM. I hope everyone's been able to watch some of these presentations and is learning lots. So today, as I said, the link between JMAG and PSIM. PSIM being a tool for power electronic simulation. Where's my mouse? Okay, here we go. So I'm going to go over PSIM. We're going to go over the link between JMAG to JMAG Designer and JMAG RT, and also how we're supporting JMAG Express online. And we'll show the integration of PSIM and JMAG. I'm just going to get my watch down so I stay on time here. Perfect. Okay, so a little bit about Powersim. Powersim is a solutions provider for power electronics simulation and motors, so that's power converters and motor drives. We are based in the US, so incorporated in the US, and our headquarters is just outside of Washington, DC. We do have worldwide distribution. Our main distributors are, well, Powersys for one, handling Europe. And then we also have, My Way in Japan is also a fairly important distributor for us, along with some of these other locales. So definitely, if there isn't a local distributor, you fall underneath Powersim's umbrella, and we will support you. So PSIM, the first commercial release was about 25 years ago, and it was specifically designed for power electronics simulation. So that is basically our founder, Dr. Hua Jin, noticed there was need in industry for a tool that could deal with the switch transition properly. So when you turn a switch on or off, so an IGBT, MOSFET, or what have you, that introduces a derivative into the voltage and current waveforms, and that derivative can cause issues with regards to convergence, without naming names of competitive tools. But that transition and those derivatives can cause problems. So PSIM set about to properly simulate or better simulate how a device turns on and off and deal with the resulting convergence and math and differential equations. Again, so purposely developed for power electronics. And we are widely regarded for simulation speed, result accuracy, and robustness. Result accuracy, even better when we link to JMAG. So when it comes to motor drives. So some basic idea here is that PSIM it fits between the system control world of MATLAB Simulink and the device world of SPICE. So SPICE being specifically developed for integrated circuit analysis, and MATLAB Simulink being this all-encompassing simulation tool that sort of handles power electronics, but that was never their sole intention when MATLAB Simulink was developed. It's just sort of something they do. Whereas PSIM purposely, whoa, what happened to my screens? Did my computer crash? Am I back? I just had a black screen incident.
We are able to see your screen.
Okay, yeah, all my monitors just went black for a second. Okay. Yeah, so here we go. So this is the design space of PSIM, our ecosystem, and essentially we're trying to push through the design, simulate, and implementation world. So we link to several different tools: Smart Control, Ridley Works for control loop design stuff. And then we also have our own design suites for motor control. So a motor control design suite and a hybrid electric vehicle design suite. And we'll show how these works in my examples in a little bit here. And then I've also got, we do power electronic simulation. So we do thermal loss calculations, digital control. We can do battery models and PV models if you're into that sort of thing. We do link to Simulink. So if you have existing simulations or control structures defined in Simulink, we can simulate the power stage in PSIM. We do link to LT Spice. And of course, importantly, the link to JMAG here is what we're going to talk about. So both a link to JMAG Designer and to JMAG RT. whoop. And then when it comes to implementation, PSIM does embedded code generation for these TI targets up here. So this the C2000 product line mostly. And then we are also generating code for a mixed DSP FPGA development system called the PXpert4, which is developed by MyWay in Japan. And then there's some VHDL stuff here. And then also you can export your power stage and then run that with your control code running on hard here and link that to the Typhoon Hill and do a hill simulation with the power stage. And so there's all sorts of options when it comes to connections and links and all that kind of stuff. But let's focus on the motor drive things for now. So the PSIM JMAG link. So essentially it's probably what you're expecting right now. PSIM provides the power stage and then JMAG provides the motor. So when it comes to the power stage in PSIM, we're talking about switches, either ideal switches or thermal device models. Those thermal device models would provide us with switching loss calculation, and they would also provide us with thermal, heat sink modeling. So we could look at modeling a heat sink and then seeing what our junction temperature ends up at. We could also look at how those all kind of interact there. We can switch to a non-ideal device model, and we can drive a more realistic switch waveform down the line. What else can we do? You can, with the thermal models, you can compare IGBT versus silicon carbide versus MOSFET versus GaN. So all you need to do is bring in that model from our database, or if it's not there, it's pretty easy to rebuild a new one. And then importantly, we can also generate scripts. So you can define a script to run a simulation through all sorts of design scenarios. So you could say, okay, I want to compare these 3 devices and I want to run this script. And then at the end of it, I want to compare the switching losses on them or what my junction temperature gets to if my heatsink stays the same, those sorts of things. Or, run it at different DC bus voltages, see what kind of torque profile you get, speed torque profile you get when you switch to field weakening during acceleration, all that kind of thing. And then obviously we're linking to the JMAG model. So we're either linking in a specific co-simulation with JMAG. So when you'd be running PSIM, we'd be asking for FEA convergence at every step. So that's with Designer. When you're running that, obviously you're looking at a longer simulation because we're requiring the FEA to converge and solve at each time point. But with the RT models, it's still nice and quick like a regular PSIM simulation. So you'd be getting results within a few seconds to a minute if it's a bigger or longer simulation. So again, I just kind of copied over this a little bit here. So we're talking to, so we have 2 modules. So we have the PSIM MAG coupler module, which links between PSIM and JMAG Designer. And then we have the PSIM MAG coupler RT model, MAG coupler RT module, which links to the JMAG RT models. The MAG coupler RT link supports all JMAG RT model types, including PMSMs, step motor, solenoid, linear sync, induction, wound field, 3, 4, or 5 switch reluctance, or the generic models. We just recently tested the generic model with like a 6-phase PMSM. This functionality is new for us. The old link that had been around for years, if you're familiar with the MAG coupler RT link with PSIM, only was supporting a couple models before, mainly the PMSM, and we recently expanded it to the full library list here. So this is kind of how it works. Basically, this is the designer link. So you've got your machine drive here. If I can draw, let me get the drawing tool. Draw a pen here. So yeah, here's our power stage, characterized by the red traces. So we've got a DC bus and switches. And then down here, we've got our controller. So the controller, in this case, is doing, we can see DQ control here, field oriented control. We're generating feedback on theta over here. So the speed is coming back, and we're generating theta from this shaft speed reference. And then this model is linking out to JMAG Designer, and we're watching what's going on there. Same deal for the RT link. So essentially, instead of linking to JMAG, we're just importing that RT file, and we're just doing the same thing. So again, the RT file is nice as it delivers quote unquote the speed and accuracy of the FEA model, but at a linear model or the simplified PSIM model type of simulation speeds. Obviously, there are some things that the designer JMAG model can do that the RT model can't do. So you just kind of have to, if you're looking for specific, to look at a specific phenomenon, you need to kind of keep track of which model you need to use. And then, of course, you could do a three-way link, because if you remember at the beginning, PSIM linked with Simulink. So you could have Simulink providing the control, PSIM providing the power stage, and then PSIM then linking out to JMAG. So all of that could be possible. That would be one thing that you could do, and we do have users who do that. Importantly, someone might ask, because I know that JMAG links directly to JMAG directly links to PSIM. Sorry, hang on. Simulink links to JMAG. So there could be some questions as why you'd want to put PSIM in the middle or just use the PSIM to JMAG link. And from our experience, it's much easier to set up that link with PSIM. We can also use the PSIM's motor control design suite to close the loops very quickly. And then also, MATLAB Simulink doesn't provide that thermal module. So to come up with switching and conduction losses and heatsink design and junction temperature envelope estimation, that is not really possible with Simulink. So that's one of the reasons why you'd want to use link to PSIM. Either you could do this full thing here, but throwing PSIM in the middle here somewhere will give you a lot more information than can come out of just the Simulink part. And the PSIM interface to JMAG Express Online is pretty convenient. So we've inserted this little button here that you click that launches you out to JMAG Express. And then you can also download the machine data by clicking this little button down here. Let me bring up the laser pointer there. So you can click on that little guy there, and it'll download a specific machine model. So essentially, we're thinking that is probably one of the fastest ways to design a motor drive, where we're looking at this kind of system here where we're designing motor, export the model, set up the drive system in PSIM using our design suite. Then we can evaluate the performance, generate code, run the hill simulation, and then you're off generating hardware prototyping. Of course, obviously done within just a few minutes, because you've always got lots of hardware kicking around and there's not going to be any hiccups in here at all, of course. But that's the goal. It should be pretty seamless. But obviously we'll see. So basically the suggested workflow would be the motor and machine model design with JMAG, bring that into PSIM, use our motor control design suite. I'll show you how that works in a second. This will close the loops on DQ, D and Q current control, and then implement a speed control loop. It implements our advanced design suites implement max torque per ampere control and field weakening for you. Or as you can see here, it's just simple control. And then off to simulation. And here, let's look at some case studies. Right. Well, let's launch PSIM and discard ink. We can come back to those couple slides, but essentially I'm going to go through. So here's the linear model simulation results. Here's the JMAG Express model results. And then here's the JMAG RT designer model simulation results. So I'm going to go through I've got PSIM open here, and we'll actually go through these right away. So the first thing we would want to do, so we can use our motor control design suite to close the loop. So how that works is, well, maybe we want to design the motor with RT. So we would click JMAG Express Online. This comes up and dumps you into JMAG Express. And then, we can start working on a machine model. Maybe we've got a user file that we want already. So there's this 10 kilowatt PMSM that I've worked on before. essentially, once you've got, you would say, okay, in this particular instance, all I've done is set 10 kilowatts as the rated power. And then we've clicked evaluate. And then what happens is it evaluates that. And we end up with our characteristics here. So this is LD, LQ, et cetera. And what we would do is we would say download machine data. And then I've only got the one file. Obviously, I'm trying to keep things simple here. But that is going to push and download the data from JMAG at the back end, and then it'll dump it out to us right here, and it'll tell us where we want to save it. Obviously, I'm saving it in my little folder here, JMAG user conference parameter, so motor parameters right here. We'd click save. And here is the motor parameters. So what we would do here, so we're still kind of working on a couple things here, but what we would do is that this would automatically get loaded into the design suite. So what the design suite does, and I'll just launch a fresh version of it so we can look at what happens here. And let's pull up my little text file, is we would essentially load these values in to here. And then we would have a working machine model. So we would say, okay, we'll take RS, which is right here. So there's the phase resistance, grab that value, dump it in. Let me just put these side by side so we can look at it in action. We would grab LD, 0 point. We would grab LQ. We grab the back EMF. So our back EMF value is thousands, line to line, peak line to line at 1,000 RPM, as opposed to just the flux linkage value. Pole is the number of poles, not pole pairs. J is inertia. Let's grab the inertia values here. I need to go 0 point. T shaft is friction coefficient. Max power or torque max, or there's the torque constant, base power, base voltages. We can get all those out of the way. This is a 10 kilowatt machine. So base developed torque. So this could be 8. We'll put that at 18.12. And then max, that's 5,000 RPM. We'll just leave that there. Oh, that was going to be 100, and that was 18.12. And then we can define our control setup here, and we got some base values. So TB, we'll put that at the max value, 8.12. We'll leave that alone. We'll go IB base. It doesn't look like we've got a base value defined over here. We'll go 1 here, and then we'll go V base is 109 square root 3. Update parameter file. So all of these numbers come across, and what we've done is we've closed the loop now. So we've calculated a few things. We've got importantly, we've got DQ values, PI control values for D and Q axis. And we've got a phase margin calculated. We've got speed loop control values here. So what will happen is we should be able to, and then this plugs into our straight linear model. So we should be able to run the simulation, and we should be able to see things start up, but and start running. Doesn't look very happy. And that's because I didn't set up the rest of the parameters. So what I will get away with here is we'll just go back to this example I had set up already. And there's a few things that are in here that are different from the base value of the design suite. But essentially, so I think the DC bus voltage here is different. We've got different switching speed and all that kind of stuff. So we've got a few different parameters from the base value. But essentially, it's the same again, where we bring across these values, and these values then we get calculated. and we bring in D and Q control values, and we can just run the simulation. And we're going to see, so here we are, the shaft speed is ramping up. We can take a look at the current flowing. And obviously this is a linear model, so everything looks really nice and peachy. We'll just wait for that to finish. And so there's the generated torque. We've got our three-phase currents, IS, IS, BC. We can see we went into field weakening right here. And then we can pull up the DQ control values. We can pull up the IQ control values. We can see where we're running at max torque per ampere, and we switch over. So we switch over to field weakening right here, just after 20 milliseconds. So there's the field weakening action. Then we get to steady state values over here once we hit, I'll pull up over here, once we hit reference speed of 5,000 RPM. Okay, so everything looks pretty good there. And then the next step would be to change this machine model and run with the Express model. Okay, so here's the JMAG Express. So all we're doing is pointing to the RTT file here. So we would just grab that, if I open up my folder, so we can look at my bits here. So we've got the RTT file in here. And so basically the RTT file is what's providing us the background information. So there's a couple things we need to put in here, but then there's all these flags we can set for extra information. So we can run this simulation now, do sort of the same thing. We see that this is working at a relatively similar simulation speed. Let's pull up the other phases here. So as this is simulating, let's look at the options here. So we're looking at the moment of we've got the current flag, the back EMF flag, rotor angle flag, speed, torque flag, power loss flag. We don't have the, we're not including the power losses into it. And then we've got a mechanical master save flag. So once this is over, we should be able to look at a few different things from the machine. Give it another moment. So it's not quite as fast as the linear model to begin with, but it's pretty quick. And especially compared to like the designer file, if you were to run with JMAG. So here's, let's go back and pull up these ones. So there's our three currents. So this one is the Express model. So it doesn't have spatial harmonics. Where's the generated torque? So here's the generated torque. So still relatively smooth. We do, I mean, we are showing a switching ripple. I want to make that clear. So there is still the switching ripple in there. So it's not a completely smooth torque. Switching ripple is also in the PSIM linear model. And then we can pull up, so here's some loss information. We can see how many watts we're getting loss and eddy and hysteresis. We can pull up, here's the back EMFs. So all that is there. And then the next one, obviously the slightly more advanced version of this would be to bring in the RT designer file. So this one then would be, I paused that simulation. Let's run this one. So same deal now. This is now with the more advanced model from the more advanced RT model. So this is the one that's come out of designer. We can see this one ramping up. And it's all working off the same set of parameters. So all three of these files, if I go back, sorry. All three of these files are working off the same set of parameters. So it's a common text file with the control parameters, and those control parameters were originally developed or with the PSIM linear model, And then we've gone and just clicked, update parameters. So it's the same set of system parameters across all three, and control parameters also across all three simulations. And here we are. Got the output. Waiting for my results to load. So here we can see, we've got some more options now to look at. So there's the flux, more loss information, generated torque, TEM. Now we're seeing a lower frequency ripple here. Now because we've got some other more interesting phenomenon going inside of this more detailed modeled. Let's look at the currents. Okay, so and then I talked about switching to a thermal model, so we could come in here and very easily just pull this guy out. I'm just going to hit disable there. Let me clear this up. And we would come into our database, grab a thermal module, say we wanted to drive IGBTs here. Oh, okay, I'm actually running a beta version of PSIM. So the thermal devices aren't loading in right now, but essentially I could just launch another version of PSIM here that's non-beta. It looks like my DLL isn't loading with the models, but essentially we would just drop in thermal, grab IGBT, and we could say grab here's a Fuji 6-pack IGBT, and this gives us the switching and conduction losses that we would want. We would connect it up, set up the drives, and then what this model does is it idealizes the switch transition, and then it will interpolate off of that into our device database editor. And so let's pull up that same, it was a Fujitsu part, or Fuji, it was a Fuji electric part. So we've got this 6-pack. So here's the conduction losses. And so we would push the losses out into a thermal equivalent for the heatsink, or you could fix the junction temperature, whichever. If you use the heatsink model and we end up at junction temperatures between 25 and 125, it'll interpolate between those 2 points and constantly update what the losses are. When we come to the switching losses, again, we're looking at different losses at different temperatures and collector currents and voltages across the device. And those will all get scaled properly as well. So the switching losses will just be calculated. So we're not integrating the voltage and current. So it's an ideal transition. So we can end up with simulations that will happen in a reasonable period of time, nice and fast. And then we can start, comparing this IGBT versus the silicon carbide device if we wanted to look at that justification, or look at how hot our motor gets during certain drive cycles or during acceleration or all those sorts of things. So I think I am kind of close to the end of my time. Are there questions that I can answer, or I can show a little bit more of the simulation stuff?
Sure. Thank you very much, Albert. Let me see if there are any questions. If you have any questions, you can always post it here. Let me check. Okay, interesting. We do not have any questions yet, but
no question. Okay. I can show some of the other things that one can do. So next up then, obviously, so we looked at the thermal model that can be swapped in. We can also switch these device models out, and we can go to a level 2 model. This is now a non-ideal switch model. So this helps us to kind of start adding in a realistic switch transition. So this would be modeled after a particular device. And then sort of plugging down along that path of adding in interesting things to study. The next thing to look at, now that we have a somewhat realistic switch transition, is maybe we would want to add in now a realistic cable model. So this would be the next thing to look at. So here we have this, and this is a distributed model. So we could model a cable with 10 sections, and this is implementing this, I don't have the figures here. Let me put the model down with this one. So here we have this, and so we're implementing a distributed RLC model with coupling capacitance between the phases. So what this model will do is we can insert that now between the motor and the inverter. That coupled with the realistic switches, we would then start to see interactions between the motor and the machine and the cable, and we would this can provide some really interesting insight. Obviously, as we start adding in more realistic models, the simulation time will increase. And I think the designer file contains the coupling or the parasitic capacitors, were the more interesting high frequency coupling to chassis ground. And that would be, that coupled with this model would really give you a really good interpretation of what sort of filtering you need to provide on the front end here, especially as you go to silicon carbide devices here, which have a very fast dV by dt. As you introduce that into the cable, there's going to be a lot of kind of crosstalk. So there's this kind of study is really important. So as you start adding in detail, you know, that it's all kind of triggers off of the original sort of ideal simulation, switching in more realistic machine model, switching in more realistic switches or thermal devices, and then changing this this ideal connection here to a non-ideal connection, and then as you keep it going further, then changing the front end here from an ideal DC source to one to maybe have a listen network out there, or front end filtering, or even a DC bus transmission line model as well, to mimic how your actual machine is an inverter and power electronics are sitting in their actual prototype or developed product state. So all that can be looked at. You know, importantly with PSIM, we can look at, if we look at, say, the current here, let me do that on a new screen. New window, ISA. So we can run FFTs of this. Let's look at the dB microvolts. So we can run FFTs quite quickly and look at the harmonic content of that current. You know, if I come back over here, let me just add in a DC bus cap over here, and then add in some inductors, and I'll make those level 2. So we'll make that a really tiny inductor, so 20 nano with a little bit of series resistance, 0.1 milli, let's say. And we'll copy that over. What's the DC bus value? So we'll pre-charge the cap. We'll make it nice and big, 200. We'll look at the voltage and current, and maybe we'll go to level 2 on this one and add in a little bit of ESR, say 10 milliohms. And we'll connect that up. So now we can run simulation, runtime graphs. There's the current in that cap. And then obviously, as we get a more and more detailed model out here, or as we add in the non-idealities out here. So this, I think, is usually pretty interesting for people. Let's run the FFT of this. Let's go to the dB microvolts. one of the important things to look at here is, people care about conducted emission standards, and we can see, we can overlay, say, the FCC Class A or Class B standards on that capacitor current, see what that looks like. I should have set it up. Let's actually look at the source current. So we'll look at the current flowing through that inductor, rerun the simulation. Because PSIM is so fast, and we could be doing this with the RT models too, it's very easy to add in extra stuff, rerun the simulations, and come back and see what's going on. And we can look at this now. Okay, let me just add on to this one, the inductor current. So we can see the inductor current profile in pink there. We can see the FCC Class A standard. Let's zoom in over here. Let me make that thicker. So there's the FCC Class A. We have a whole bunch of other standards you can look at. So there's some mil-spec standards, or you can define your own to see what kind of harmonic content you have and whether or not that's a problem and what kind of filtering you need to provide. Okay, Ved. Any other?
Hey, Albert, thank you very much. I think we got multiple questions now.
Yep.
We'll take a couple of them right now. So one of the question is, can PSIM use different time rate for on multiple components? For instance, run motor block with 0.1 microsecond, but run thermal with 1 second?
No. So the PSIM simulation engine runs everything at a fixed time step, or you can run a dual time step, which forces a smaller time step at the switch transitions. What you can do as part of scripting is run your whole system to steady state with a coarse time step, and then switch to a smaller time step once you've hit, if you want to look at other things. So through scripting, you can use initial conditions and run the simulation to different points and use different time steps. But at this time, we do not allow specific parts to run at different time steps.
Okay. Thank you for answering that. One other question is it possible to feedback temperature from thermal model to a motor model?
Is it possible to feedback temperature from the thermal module? So our thermal module so our thermal model is this guy here, and this node provides the losses. So on this node is going to be all the combined conduction and conduction losses from all the devices. So if we put a temperature probe on this, we'll look at the temperature there. And then internally, there's an RC network from junction to case, and we can look at the temperature of the junction and case separately. So we can use this value. We can feedback on this for sure. So we can say, okay, what's my junction temperature? And then or what's my case temperature? And then I can feedback on that and then make decisions about limiting torque in terms of our control algorithm. That can be done. When it comes to the RT model, we have, I think, these nodes at the bottom are providing temperatures. Or those are TMAG and T-coil. I think those are temperatures. And you can definitely, those are control signals, you can bring those up.
Perfect. All right. So let's see. I think we're
I just got a note from a colleague. Yeah, those are definitely the temperatures, and those are usable in simulation. You can adjust based on that.
Mm-hmm. Yes. Perfect. Thank you very much, Albert. We do have a couple of more questions, but I think we'll just take them on the app because we are a little running over time.
Okay.
Thank you a lot for your participation and for a wonderful presentation showing us seamless integration between JMAG and PSIM. Thanks, Albert. We will switch to the next session.
Perfect. Thank you so much, guys. Everyone has my email address, and I'll hop onto the app. I'm not on it yet, but I'll download the app right now, and I'll make myself available to answer a few more questions. Okay.
Thank you.